We have seen in a previous video that the decision tree tries to separate the two classes by taking a decision right somewhere in the middle of the two classes. So decision tree tries to split the data in such a way that the two buckets which are created are entirely consist of one of the classes. This is what the decision tree tries to. It may not be successful in all cases. Sometimes it might be impossible to separate the two classes, but that is the goal of a decision tree. It tries as much as possible to separate the two classes, to separate the pluses from the minuses. So it takes a decision, or it makes a split in such a way that pluses are separated from the minuses. Now let us understand the theory. Let us define the theory behind the decision tree and see, and then we will look at the maths that happens at the back end. So the objective of a decision tree, let us see what the objective of a decision tree is. The objective is to create splits on independent variables. Remember, we were splitting the independent variable, not the dependent variable, okay? So the splits were being made in the independent variable space. So in the previous example, we split it on x1 and x2, not on y. Y is our plus and minus. Why? The separation of plus and minus is the result of the split, but the splits are actually being made on the independent variables. So create splits on independent variables to form pure or homogeneous buckets. What do I mean by pure or homogeneous buckets? So buckets which entirely consist of either pluses or minus. So this is what the decision tree tries to, but it may not be successful all the time, but that is the goal, so that it can form pure or homogeneous buckets. Or I can say buckets which have more of one class. So more of ones or more of zeros. So even a situation where you have, let's say we have a situation where we have two pluses and two minuses in the same bucket. Now this is the worst form of impurity. This is an impure bucket. Why impure bucket? Because both are equal in numbers. So it is 50-50. This is the worst form of impurity. So what is, even if I am able to make it like this, let's say 1 plus and 2 minus, this is better. This is still pure compared to that, because I have 2 minuses here. I have 2 minus, so I have more of one class and less of the other class. Similarly, even if I am able to form 2 plus and 1 minus, this is better than this one. So this is worst. This is better. And even this is better. Compared to the first one, 2 and 3 are better because they have more of one of the labels. This has equal number of both labels. This is the worst form of impurity. Of course, if you can get to this level, number 4, this is the best. So this has zero impurity. Why zero impurity? Because both are pluses. There is no impurity here. It is entirely made of pluses. So that is the goal of a decision tree, to ultimately reach to this stage. Sometimes it may not be able to reach to this stage, but at least it will come till this stage. So it will move out of this worst form of impurity. So that is the goal of a decision tree. And where are the splits made? We have seen the splits are made at the midpoints of consecutive pair values of independent variables. So I intentionally splitted this at 2.5 because it was midpoint of 2 and 3. Otherwise we can draw infinite number of lines between 2 and 3. So there would be a confusion that which line to select, because there can be infinite number of lines and all of these lines will be able to perfectly split the pluses from the minuses. So which line do we select? We select the line which passes right through the middle of the consecutive points. Now the question is, how do we measure impurity? So we were talking about creating pure buckets or uniform buckets or homogeneous buckets. How do we create them? Now a computer will not draw plots like this. So this is for human understanding that I have drawn this. A computer will not draw plot like this and then decide where to split. Or imagine if you have 10 independent variables, then your data would be into 10 dimensions. Coming up with a plot and then figuring out where to split would be almost next to impossible. So how do we do that in that case, or how does a computer do that? So that is where we go to the underlying maths of a decision tree. We have a variable, a parameter called Guinea index. So Guinea index is a mathematical parameter which measures the impurity in a bucket. So Guinea index is a mathematical parameter which measures the impurity in a bucket. Remember, it measures the impurity. And what is the goal of a decision tree? The goal of a decision tree is to form pure buckets. So the goal would be to minimize the impurity, to minimize Guinea index. The goal of a decision tree would be, let me write it down here, it would be to minimize this quantity. it would be to minimize the value of Guinea index, and as it minimizes the value of Guinea index, it indirectly increases the purity of the bucket, which is the goal of a decision tree. Now, how is Guinea index measured? It is a mathematical quantity which is measured by this formula, 1 minus summation of pk whole square. Now, what is pk? Pk is the proportion of each class in each bucket. We will see this with an example in details, but this is the formula. It is the proportion of each class. So if you have a binomial class, it is the proportion of zeros and the proportion of ones in each of the buckets. If you are splitting into two buckets, you will calculate the proportion of 0 in bucket 1 and proportion of 1 in bucket 1, and then similarly you will calculate the proportion of 0 in bucket 2 and 1 in bucket 2. And m represents the number of classes you have. So we usually deal with a binomial classification problem. In that case, m will be equal to 2 in case of a binomial classification. Now let us see this with an example. Let us see how do we calculate Guinea index and how does it help a decision tree come up with the appropriate split with an example. So let me take a very small data. I'm taking a small data because it involves manual calculation. The computer does this for us, so we don't need to do this. But to understand the maths, this is important. So let's say this is our data. I have two variables, x1 and x2, and so where would we split here? We have already seen this example. We would probably split at somewhere here. Somewhere here we would split, and this would give us pure buckets, exactly pure buckets. Now, why did we split here? Because the Guinea index, as a result of this split, we will see now that it turns out to be the least. And remember, that is the goal of a decision tree, to minimize the value of Guinea index. So let me write down the goal. The goal is to minimize the value of Guinea index. And we will see now that once I split here, the Guinea index will become the minimum. Now let's say somebody else does not agree to this and he says that no, I will make a split, let's say here. He is adamant on making a split here. He makes a split here. So I will calculate the Guinea index for both green split and the red split, and we will see which gives us the lesser value of Guinea index. And whichever split out of green and red, whichever gives us the least value of Guinea index, we will be selecting that split. So let's calculate. Now before we in fact go ahead with a split, let us calculate the Guinea index present in our data entirely before we split. So what we try to do using a decision tree is we try to reduce the value of Guinea index, or we try to reduce the impurity. So first we will have to calculate what is the impurity that we are starting with so that we can reduce it further. So let me write it down here. I'll write before split. So let me use the same formula, 1 minus summation of pk whole square, and before split I do not have any split, so all the points are in one bucket, the entire data is in one bucket. So how will I do this? 1 minus, this is the proportion, so proportion of plus, let me write the proportion of plus whole square, and then since I have a summation sign, I will write proportion of minus whole square. So let us calculate this. 1 minus proportion of plus whole square. What is the proportion of plus? I have 1, 2, 3, 4, 5 points in plus, and total I have 5 points in minus also. So the total becomes 10. This is the proportion, remember. So it is 5 by 10 whole square, and once again I have 5 by 10 whole square because I have 5 plus points and 5 minus points. So this gives me, so 5 by 10 into 2. So this will give me 2 into 1 by 4. So this will cancel out and it will give me 1 by 2. So 1 by 4 plus 1 by 4 will give me 1 by 2. So it gives me 1 by 2. So I get 0.5 as the answer. So this is my Guinea index before split. Now remember, I briefly talked earlier that this is the worst form of impurity you can get, where you have equal number of pluses and minuses in the same bucket. Remember, before split everything belongs to the same bucket. I have equal number of pluses and minuses in the same bucket. This is the worst form of impurity, and the worst form of impurity is giving us a Guinea index of 0.5. So what does this tells us? This tells us that the worst value of Guinea index, or the maximum value of Guinea index, is 0.5. Guinea index cannot go beyond 0.5. This is the worst form of impurity. Now let us go ahead with the split. Now after split, now let us see which split is better. First I will calculate the Guinea index for the red split. So let me calculate for red split first. So the red split happens here. I have two buckets now. In the red split I have, let me call this bucket 1 and this bucket 2. So first I will calculate the Guinea index for bucket 1. So bucket 1, what is the Guinea index? It is 1 minus. Now proportion of plus in bucket 1, how many pluses do I have? 1, 2, 3, 4. I have 4 plus in bucket 1, and total how much do I have? I have 5. So 4 by 5 whole square plus I have 1 minus, so 1 by 5 whole square. So this is the value of Guinea index. Let me directly take it. 4 4 are 16 and 1 17. So this is, let me calculate this quickly with a calculator. So 25 minus 17 by 25, it gives me 0.32. So this is the value of Guinea index in bucket 1, 0.32. Similarly, I will calculate the Guinea index in bucket 2. So let me quickly do this. I have 1 plus and 1, 2, 3, 4 minus. So this is similar. I'll get similar answer because this will come here and this will go there. The proportions interchange here. So I think I'll get the same answer here as 0.32. So this is the Guinea index in bucket 1 after the red split, and this is the Guinea index in bucket 2 after the red split. So the total Guinea index after split, total Guinea index after the red split, Now how do we calculate the total? We don't just add them up, we take a weighted average. So weighted average, weighted by the number of points they have. So the number of, let me write the formula for that. The number of points in bucket 1 into Guinea index of bucket 1 plus number of points in bucket 2 into Guinea index of bucket 2, and all of this divided by total number of points, so n total. This will be the Guinea index after split. Okay, so let's calculate this. What is the number of points in bucket 1? I have 5 points, so 5 into 0.32, and here as well I have 5 points, so again 0.32 into 5 divided by total 10 points I have. So how much would this give me? So 5 plus 5, so it would give me the same answer as both has equal number of points. So I would get a Guinea index of 0.32 after the red split. So see, the Guinea index reduces. Initially we started with a Guinea index of 0.5, and even the red split reduces the Guinea index, so it does reduce impurity to some extent. It reduces it to 0.32. But remember, we will select that split which gives us the least value of Guinea index. So let us see what Guinea index do we get after doing the green split. So now let's calculate the Guinea index with green split. So again, even when we do a green split, we divide the points into two buckets. So this is my bucket 1 and bucket 2. Let's calculate the Guinea index for the first bucket. So we can see the first bucket has only minuses. I have 5 minus points. So let me calculate for bucket 1. I have 5 minus points here. So remember, I will write the proportion of 5 minus points divided by total. I don't have any plus, so it is 5. And I have 0 plus points, and total is also 5. So I'll do this. This is the Guinea index in bucket 1 after the green split. So 1 minus 1, it gives me 0. So the Guinea index is 0 in bucket 1. Similarly, if you calculate for bucket 2, again bucket 2 has only plus points. So again this will interchange and I will get another 0. So the weighted average of 0 and 0 is again 0. So Guinea index after the green split is 0. Now what do we see? We see that we started with a Guinea index of 0.5, and the red split gave us a Guinea index of 0.32, which is less but not the least, and the green split gave us a Guinea index of 0, exactly 0. So this means that the green and Guinea index cannot go below this. This is the purest form. You can see it is the purest form. We have entirely split our labels into pluses and minus. So this is as pure as it can be, and the Guinea index for that is 0. So this tells us that the green split is better than any other split. So we tried with 1. You can try with any other split in this case. None of the splits will be as good as the green split. So the green split is the best one, and hence the decision tree will select the green split. So this is what the algorithm does. Once you run the algorithm using codes, which we will see in a later video, the algorithm will try all possible splits and finally select the one which gives the least value of Guinea index. In some cases it may not be able to arrive at the final Guinea index of 0, but the Guinea index, whatever it arrives at, will definitely be lesser than what it started with. So the Guinea index after split will definitely be lesser than the Guinea index before split. So this is how it works. This is how this is the maths behind a decision tree algorithm.